Thanks, Bob.
I'm not sure what time zone you're in, so let me begin by saying good morning, good afternoon, and good evening. I count myself as being extremely privileged to have worked with the great Rodney Baxter from 1980 to 1985. In addition, I was seconded to ANU for 1 year in 1989, the special year in mathematical physics. And I must say, these years were magical years. And this very much shaped my career. In fact, I learned the subject of exactly solvable models by reading Rodney Baxter's book, but it wasn't even published yet. So I learned this subject matter by proofreading Rodney's book. And it was somewhat of a feat because my habit was to read the text back to front so that I would read what was actually written rather than what I expected to see. So I managed to remove quite a few typos from that book. But of course, Rodney was very exacting, so there were not so many typos for me to pick up on. So I will gradually move this conference to the science. And, you know, Rodney was very passionate about doing his sums. Rodney was a modest man. He saw his job was to calculate partition functions, and these are just glorified sums. Of course, he did his sums in a very, very elegant way. And he's given us a toolbox of magical tools that we can use and apply. And so I'd like to talk about some of my recent work with Johan Rasmussen, which connects with conformal field theory. The title of the talk is Ocneanu Algebra of Seams, Critical E6 RSOS Lattice Model. So I think Rodney would enjoy this talk because it's on his beloved restricted solid-on-solid models and using transfer matrices. And some of it is in rather a pedestrian way, which I think he would also appreciate. So let me give some history of this subject. It all starts, of course, with Andrews Baxter Forrester. So this was 1984. It's the start of a lot of developments in mathematical physics. So Andrews Baxter and Forrester created an infinite number of what's called now A-type minimal models. And then Pasquier, Vincent Pasquier, came along and generalized these to ADE. These are the Dinkin diagrams. These models are based on Dinkin diagrams of simple Lie algebras. So he generalized this list of models. Then from a completely different perspective, based on pure mathematics, Ocneanu came along in 95 and said, well, these lattice models are connected to CFT, and CFT in the bulk has 2 chiral copies of Virasoro, and these are joined in a very special way. And studying paragroups and some very fancy pure mathematics, he came up with diagrams like this that describe the bulk theory, how the 2 halves of the conformal field theory are glued together. So these are called Ocneanu diagrams, or named after him. And I'll show you some more later. Then Petkover and Zubair came along in 2001. And for these models, there is a lattice model, and in the continuum scaling limit, it describes the conformal field theory. They gave the generalized twisted partition functions. So that's partition functions on the torus in the presence of defects. Cockrow and Scheiber put this into a more mathematical language. And some colleagues of mine in Melbourne, we also looked at this from the point of view of the lattice model, building in these defects, these seams as on the lattice. And that brings us to the latest paper. These topics are still very much alive. I think there'll be a lot of years in the future where there's still active research and things to be learned about these RSOS lattice models, connections to CFT, and connections to many other topics in mathematical physics. So this is what I'm talking about today, realizing Ocneanu's abstract algebra concretely on the lattice in terms of integrable seams. And because I only have 30 minutes, I will focus on one of these infinite families of models, an exceptional case, which is related to E6. And if you look carefully here, you'll see a red diagram, which is the Deacon diagram of E6. And there's a blue copy here, and there are 2 more copies in that Ocneanu graph. So these lattice models are built from the data of ADE simply laced Lie algebras. And we have an A family, 2 Ds, and 3 exceptional E's. So these are infinite families, and these are exceptionals. I want to focus on the E6, but let's start with the AL. These encapsulate the Andrews-Baxter-Forrester models. If you look at D4 here, this is critical 3-state pots, and so on. These look like very simple diagrams, but they encode a lot about the lattice models and the CFT. Each graph comes with a Coxeter number G, a list of Coxeter exponents, one for each node on the lattice. These graphs come in various types. There's type 1, the simplest to work with. A, D even, E6 and E8 of type 1, but D odd and E7 of type 2. And these diagrams have certain automorphisms, symmetries. Usually a Z2, E7 and E8 have no symmetry, but the very special case of D4 has a 3-fold symmetry. In fact, it has S3 symmetry. And this plays an important role, not just in the lattice models, but in the associated conformal field theories. So the node 1 labels the identity. We will start on the left with the node labeled 1, the identity operator. It has a unique neighbor labeled by 2, and this is called the fundamental. And what these graphs are encoding is fusion. Fusion is a very important concept in conformal field theory, but it's also very important in these lattice models. You can think of graphs, or you can think of their adjacency matrices. The eigenvalues of the associated adjacency matrices here all are of the form 2 cosine m pi on G, where m is one of these exponents. So you can ask yourself, all these eigenvalues are strictly less than 2. You can ask yourself, which graphs have all eigenvalues less than 2? And the answer is this list and only this list. So this is a list of very special diagrams. So let's describe some fusion. Of course, you're used to fusion in the sense of spin half by spin half gives the identity plus the spin 1. We're going to generalize that. In general, fusions are described by graphs and in terms of graph fusion algebras. The simplest graph fusion algebra is well known from CFT. That's the Belinda algebra. You take the adjacency graph of the Andrews-Baxter-Forrester models. That's just a linear graph AL. Dimension L by L. You start with the identity. The fundamental is the adjacency graph of the A diagram itself. And then you operate with this recursion. You define these recursively, and at some point you find it stops. You get to NL, and that's a Z2 symmetry operator, interchanging the heights along the diagram, and then you get 0. So you can solve this recursion. It just gives you the Chebyshev polynomials of the second kind. So all these matrices commute. They're all functions of the fundamental. Then when you look more closely, you find they satisfy a nice closed simple algebra. Ni by Nj can be written as a linear combinations of the nks again, with the k's with the nodes of the diagram AL. And the structure constants are nothing but the matrix entries labeled by J and K of the ith matrix. So that's a very simple algebra, a finite algebra, but it encodes all the information you need to understand fusion in these models. So the first model you might think of is tricritical easing model. This is A4. The Coxeter number is 5. You start with the identity. Here's the adjacency matrix of a linear graph with 4 nodes. Now you apply this recursion. Here's N3. N4, you see it's just a Z2 involution. So that's sigma, and then N5 vanishes. The next thing you can do is generalize it. So far, this is just the A-type diagrams, but the D and E lattice models were introduced by, at least critical models were introduced by Vincent Pesquier. And so now you can look at the same recursion, but instead of starting with an A adjacency, you can start with a G adjacency. For example, it could be the one for critical three-state pots, which has branching in three nodes around the exterior. So again, you start with the identity. Now you take the adjacency matrix for D4, here it is. And now you start applying the same recursion. You get N3, and then you go to the next one and you come backwards. This is N4, and then N5 is the identity. So it closes, and it satisfies the same sort of algebra with the same structure constants, the structure constants of the entries of the Verlinder matrices, and you have a closed algebra. And these little n's, as opposed to the capital N's, are called fused adjacency or intertwiner matrices. Now these fusion matrices are called NIMRAPs, non-negative integer matrix representations. And for any type of fusion, you always find NIMRAPs. Next, let's move up a level. Let's move now to the graph fusion matrices, which were introduced also by Vincent Pesquier. Now what you do is, again, you start with the identity and then the adjacency matrix of your graph. But this time, when you do the iteration, you do it according to the branching of the graph itself. So the structure constants here are related to the adjacency matrix of the graph itself. When you do this, you generate a number of matrices now denoted by n hat. And again, they form a closed finite algebra. But now the structure constants are given by the entries of n hat. So it's a very similar sort of fusion algebra, but again, it has some physical meaning. Now there's compatibility between the different kinds of matrices, in particular the n hats and the little n's. You can multiply a little n by an n hat and you get a linear combination of n hats. You can write the little n's as a linear combination of the capital N hats. And these coefficients, you see, I put a 1 here. So this is the 1/8 entry of the n-ith matrix little n. So this is a compatibility, and this is called the intertwiner, fundamental intertwiner relation. And for E6 that we'll focus on, the rectangular fundamental intertwiner, that's these matrices here, admits a generalized left inverse. That means this relation here can be inverted to write the capital N hats in terms of the ni's. And for E6, there's no difference between capital N hat and little n for a equal to 1, 2, and 3. But as you move along the E6 diagram, you then branch, and then you get these relations. N4 hat is N6 minus N2, N hat 5 is N5 minus N3, N hat 6 is N2 plus N4 minus N6. So you can move backwards and forwards in this type 1 case between the capital N hats and the little n's. These capital N hats, this algebra only exists for type 1 theories. In the case of type 2, there is no proper graph fusion algebra with non-negative integer entries. So here's the Ising model. This should be most familiar. You have 3 operators: the identity, the magnetization, and the energy. That's I, sigma, and epsilon. Here are the fusion rules for the Ising model, and they're realized by the fusion matrices n hat. Because this is a an A-type theory, there's no difference between the hats and the non-hats. So these are the only 3 matrices, 3 by 3, and you verify this closed set of fusion rules for the Ising model. For 3-state function, you now start with D4. Here's the adjacency matrix. N1 hat is the identity. And now you fuse up and you get N3. Notice that this is not a symmetric matrix. You notice that 2 is fixed. That's the node in the center. And the other 3 are permuted around. This is a Z3 permutation. So you think of this as omega, and n hat 4 is omega squared. You rotate in the opposite direction. And here's the Cayley table for multiplication of these 4 matrices, I, N2, N3, N4 hats. And it closes in this simple way, which is symmetric. So this is a commutative algebra. There's another element which doesn't occur in the graph fusion algebra, and that's the Z2 complex conjugation symmetry. This just interchanges 3 and 4. You could add that in and write a larger Cayley table, and that would no longer be commutative. Here is the intertwiner. It's a non-square matrix. It's rectangular, and it just consists of these matrix entries. And this tells you information about the conformal field theory because it tells you there are extended characters, 1 + 5, 2 + 4, and then 2 copies of 3, 3 and 3 star. This is this occurs in the conformal field theory description of critical three-state pots. Now let's move across to the lattice models, ADE lattice models. You start with the Boltzmann face weights. There are 4 heights around the elementary face of the square lattice. The weights of the faces depend on the spectral parameter u. We have trigonometric functions. Lambda is just pi on the Coxeter exponent. And the square roots of these sides, and we have some Kronecker deltas. And these weights vanish unless the product of all these entries of the adjacency matrix, this must vanish if this is equal to 0, which is to say, each of these edges must be a allowed edge on the Dinkin diagram of the model that you're looking at. Now, these face weights satisfy the Yang-Baxter equation, and that tells you that I have commuting transfer matrices, and from Yang and Baxter, we know that that means integrability. The largest eigenvalue of the adjacency matrix is just 2 cosine lambda, which you can write as 2 subscript x in this little box. And you can look at the eigenvectors of those adjacency matrices for G, and the eigenvectors take this form, where these symbols AX defined here just are the quantum dimensions for these models. And this is the form they take. And for G6, we're looking at this row here. Now we're going to do something special. With these weights, we're going to go to certain limits. We're going to take the spectral parameter to either plus or minus infinity. Now, why do we do this? Because in this limit, you make contact with CFT. The minus I infinity limit takes you to the left chiral component. So this is associated with the left chiral component, the CFT, and this other limit in the opposite direction is the right chiral component. These two matrices are actually inverses of one another in the sense of the inversion relation introduced by Rodney Baxter, but also by Stroganoff. And you can see that they're complex conjugates, and the x that appears here is just e to the I lambda. So these are just some specialized Boltzmann weights that will play a special role, and notice that these are complex in general. Now here's a complete set of Ocneanu diagrams that are supposed to capture the way the 2 halves of the CFTs in the continuum scaling limit are glued together. For the A case, you see that you just get a linear diagram. In general, there are 2 fundamentals. In here, we have a fundamental going to the left in red and a fundamental going to the right in blue. And they generate some fusion along a chain, and they're glued together in certain ways. But for the A case, you get back just to the Verlinde algebra. There isn't anything more to be said in that case. But for the Ds, this is 3-state pots. This is D6. Here is E6, and you can see that there's 4 copies of E6 in this Ocneanu graph. E7 and E8 is the largest case. So as I say, the red and blue lines indicate the action of the left and right chiral fundamentals labeled by A equal to 2 and 2 bar. They take you to the down and to the left with the red, and down and to the right with the blue, and just iterate to follow the fusion. So this is supposed to describe the Bob CFT. And we will focus just on E6. Now, of course, this is a graph, and associated with it is a graph fusion algebra. There are 12 nodes, and each of these nim reps is 12 by 12 matrix. So I'm not sure if your eyesight's as good as it should be. If you're young, it probably is. And you can read all of this, but you can see it in general. There are just 12 by 12 matrices here, which are encoding through these nim reps, the graph fusion algebra. So these nim reps form a non-negative integer matrix representation of the graph fusion the Ocneanu graph fusion algebra, which is here. You see this graph fusion algebra has the same structure as we've seen time and time again. The entries of these matrices are the structure constants, but this is, of course, a 12 by 12 system. There is a chiral conjugation. Here is our graph. Complex conjugation takes you from the left to the right. So 2 bar is 7, 3 bar is 12, 4 bar is 11. For everybody else, they're down the middle and they're self-conjugate. These are called ambichiral. They belong to both the left and right chiral halves. And sigma acts to conjugate from Na twiddle to Na bar twiddle. And these matrices can be written in certain block forms. Now let's move to the lattice. So usually when working with a lattice, we work with row-to-row transfer matrices. But here we're going to work with integral seams, which become conformal topological defects in the continuum scaling limit. So now we want column transfer matrices, and they come in different kind. There's a regular transfer matrix. There's the braid limit, where you replace the spectral parameter u with minus I infinity, and its complex conjugate b bar, where you have plus I infinity. And then there are these special integrable seams. Sigma k, sigma is just the graph automorphism. It's either there or it's not, so kappa is 0 or 1. There is Na with special weights and Nb complex conjugate with special weights. So this is a periodic lattice. You can see these integrable seams, which are columns, Tu, Na, Nb hat complex conjugate, and the automorphism seams. So in here we have a composite seam where you can combine sigma, which only occurs in the D cases, and Na and Nb bar. And these two relate to the left and right chiral copies of your RSOS. So these B's, you just take the transfer matrix Tu, normalize it appropriately, take the limit, and U is effectively replaced with plus or minus I infinity. So they're just limits of the commuting family here. From Yang-Baxter, we know that Tu is a commuting family of transfer matrices. The fused S-type braid matrices are denoted by NS. And now we just repeat what we did at the level of the adjacency matrices, and we can fuse. We start with the identity column, transfer matrix. N2 is the braid matrix, and then you use this recursion, but on the transfer matrices themselves. And now you build up a family of commuting transfer matrices. So we call these the fused S-type braids. So they're labeled by an index S, and this index S connects with the Katz label S of the RS Katz labels. The Na hat seams are given by the same limit combinations of NS as in the graph fusion matrices, so we can define those two. So we have these little n's and we have the capital N hats. For each ADA lattice model, these seams NS, NS bar, and Na hat, NB hat bar satisfy respectively the Verlinder algebra, which means with the Verlinder coefficients here. And for these, they satisfy the graph fusion algebra. So we built much larger representations of these graph fusion algebras. So here are the relations between the Na hats and the little n's. These are the same relations we saw before for the adjacency matrices, or NIMREPs, but now we're applying them to these commuting column transfer matrices. Now, what's important for the Ocneanu algebra is these guys, a product of an Na by an Nb, which is the complex conjugate. So this lives in the left chiral half, this lives in the right chiral half. So somehow this combination describes how the two halves are glued together. So when you look at these, you can have 36. There are 6 labels here for E6 and 6 labels there. So 36. But from these 36, you form a basis of 12, with A running from 1 to 6 and B running from 1 to 2. So these are a basis. We denote them by P's, and they run from 1 to 12. And there are these combinations of these double vertical transfer matrices. And then what you find is that these guys satisfy the Ocneanu algebra. And we verified that up to m equal to 12 in Mathematica, but you can actually prove it by diagonalization. So these p mu's or p etas, this is the Ocneanu graph algebra. And these are nothing but those 12 by 12 matrices that I wrote down longhand previously. So you can actually write down a K table of these 12 guys, and you form this 12 by 12 K table, and it exactly reproduces the Ocneanu algebra. So previously, the only representations known of the Ocneanu algebra were the NIMREPs, but now we're building representations built on these conformal defects or integrable seams. Now this accounts for 12 of these guys, but there should be 36. So what about the other 24? The other 24 are expressible as linear combinations of the 12 that are in the bases. And it's done in this way. The p's are just the products of these two, an n and an n hat, complex conjugate. But the complex conjugate just means you replace mu with mu bar. And then when you multiply these two together, it just means the structure constants mu is replaced with the mu bar. And these linear combinations give you the other 24 guys. And this represents a certain symmetry among these objects, which goes by the name of quantum symmetry. You can describe the Ocneanu algebra as a quotient polynomial ring. So you have a ring in two indeterminates, x and y, but you quotient by two relations, two polynomials. P1, which is this one, this s here runs over the exponents of E6. You look at this and you get an integer polynomial with integer coefficients. Here are the exponents. P2 is this polynomial, is quadratic. This is order 6. And if you look at P2yy, it just reduces back to P1y. And the idea is that this homomorphism maps you from P11 to the identity, P21 to x, and so on. And P12 is mapped, because this would be the identity, is mapped to y. So these are the two fundamentals, and everyone else is generated from the two fundamentals. The E6 integrable seems mutually commute. They're simultaneously diagonalizable, so the eigenvalues yield a one-dimensional representation of Ocneanu E6 algebra in terms of quantum dimensions. So you set x equal to q to the s plus q to the minus s. There's 2 cosine s pi on 12. You do the same thing with y. Q is e to the pi I on 12 here. And now you want to solve these two equations together. When you solve this one, it's order 6 in x, so you get 6 possible solutions. And solve the second one, you're solving for y, that's quadratic. So for each 6, you get 2 more possibilities for a total of 12 solutions. And here are the 12 solutions for the values of s. And you will recognize these as pairs of Coxeter numbers for the E6 graph. And in fact, precisely these pairs appear in the E6 modular invariant partition function. And that's no accident. Now, we want to be able to do algebra combining the left and right chirals. And if you multiply a left with a left chiral, that's described by the graph fusion algebra. If you multiply a right chiral by right chiral, that's also described by the same graph fusion algebra. But when you multiply a left by a right, you don't know what the rules anymore. It's not described by the graph fusion algebra. So we have to find out the other rules that you need to apply to do algebra. And in this case, there is one extra relation that comes about. It comes from this P2. You replace x and y with b and b prime, or b bar. They're the two fundamentals. You can express it this way, but this implies this relation. So when you take the square of n2 bar, you get back this linear combination. And you notice it reduces it to something that's linear in n2 bar. So now in the Cayley table, there was 4 quadrants. This one is very simple. These two are next, and then this one's the most difficult. And you identify quadrant by quadrant. Here, when you multiply out, you don't need to know anything new. It's straightforward. For these two cases, they're the top right and bottom left quadrants. Everything is fine. you only get linears in the second position, so you can do all your algebra. And then in the last case, you find that you get an N2 hat bar squared. So now you need this relation. And so now you use that relation, and then you continue, and you can work out what that product is. And now if you stare at this quadrant by quadrant, you realize what that's telling you is that these structure constants, so there's 12 possibilities by 12 possibilities by 12. So these are the 12 by 12 NIMREPs, written out in terms of Kronecker deltas and the entries of the n-hat graph fusion matrices. So this formula nicely gives you all the entries of these 12 by 12 matrices. It's not difficult to prove that this P2 B bar here actually vanishes, because you can simultaneously diagonalize this set of normal transfer matrices. And the eigenvectors are independent of U. And then it's easy to prove that the eigenvalues of B and B bar are precisely these. And so when you substitute that in, all you have to do is use the relation that these eigenvalues satisfy P2 of these eigenvalues equals 0, and that implies that that holds also for the full transfer matrices. So the proof basically follows by, for arbitrary system sizes, these results hold just by simultaneous diagonalization and using the known one-dimensional representation of the Ocneanu graph fusion algebra satisfied by the quantum dimensions. So my time is essentially up. So let me just conclude. So we argue that for critical ADE lattice models of arbitrary size M, the S-type Bray transfer matrices little ns satisfy the Linde algebra. The A-type integrable seams n hat A satisfy the graph fusion algebra. And of course, there's compatibility between those. The integrable seams, PA, PB, these are the composites with one left and one right component. They satisfy the Ocneanu algebra and the quantum symmetry. And all of these statements have been checked in Mathematica for m less than or equal to 12. Expressions can be obtained for the local phase weights of each of the integrable seams. I don't show that here. The type 1 theory's explicit expressions are obtained for the Ocneanu structure constants. So in the E8 case, you have 30 by 30 matrices, and instead of just one extra relation, you need 4, but there is such a formula for the general matrix entry of the Ocneanu E8 NIMREPs. Conformal topological defects result from the integrable seams in the continuum scaling limit. So you use this to get insight into the conformal field theory. The algebra of schemes gives a natural physical interpretation of the Ocneanu algebra. Somehow it implements the local operator product expansion on conformal defects. The Ocneanu algebra encodes how, for twisted boundary conditions, the left and right chiral halves of the CFT are glued together. Since the seams commute with the transfer matrix TU, there are, in some sense, symmetries. But some of these seams admit 0 eigenvalues, which means that they're not invertible. So these seams represent generalized non-invertible symmetries. This is the hot topic currently in condensed matter physics. The ADE models of SL2 spin half models, the simplest ones, we always start with the simplest models. The new insights give tools to systematically investigate the Ocneanu algebras of higher spin and higher rank models, for example, spin 1 or SL3 or SL2 affine ADE models. It now seems we can get a lot of insight on these defects from a lattice approach. So I thank you.